The two different metrics are important because different kinds of stimuli seem to show slightly different relationships. A city block metric can be thought of as analogous to locations in a city with a grid pattern of streets. Imagine that you measured the distance between two locations in a city by walking straight along one street, turning a corner, and walking straight along another street. In this case, both measurements contribute to the calculation of the overall distance, not unlike two right-angle sides of a triangle. City block space is generally used when the dimensions of the stimuli being compared or considered have dimensions that are perceptually separable. That is, they can be perceived and processed separately from the whole stimulus. As an example, consider two objects that differ in terms of size and color, but each dimension can be processed and considered separately. Baseballs and softballs, for example. In the United States and Canada, softball is a variety of baseball that tends to be played either casually by many adults or competitively by women and girls. The ball that is used in softball differs in some ways from the ball that is used in baseball. One of the most obvious differences is that the baseball is smaller and white. A softball is a little larger and is usually bright green. Depending on the age of the player, the ball varies in size, such that younger girls play with a smaller ball. In this example, if you are arriving at a similarity calculation among different kinds of baseballs and softballs, you can consider the size separately from the color. Although both dimensions can be considered when making a similarity judgment, they can each be perceived separately, and each contributes to its own value to the distance computation. Thus, these are known as separable dimensions. If the city block metric is equivalent to the right angles of a triangle, the Euclidean metric is equivalent to the hypotenuse. In this case, rather than walking along the right angles of the street, imagine you can pass straight through the building to find the absolute shortest distance between the two locations. Euclidean distance comes into play when the dimensions of the stimuli being compared are composed of perceptually integral dimensions. For example, consider the comparison among a whole set of objects of different colors that vary in dimension of hue, saturation, and brightness. The perception of the difference is not difficult, but being able to separately perceive a change in hue alone would not be easy. In this case, the comparisons between stimuli are made using several dimensions that are combined prior to the comparison process. As a computational technique, MDS is more complicated than what we can discuss within the scope of the chapter, but the basic idea is that if a subject provides similarity ratings, as discussed earlier in the chapter, the MDS algorithm will compute the minimum distance among all concepts and describe these distances along a number of dimensions. The algorithm can specify two or more dimensions, but the best fitting model is the one that maximizes the solutions with a minimum number of dimensions. So typical MDS solutions involve 2 to 3 dimensions. Figure 2.1 shows an example of a multidimensional scaling solution for birds. A graph like this would be created by asking participants to rate the pairwise similarity between all possible items. In other words, you would rate the similarity between a goose and a duck, a goose and a chicken, a goose and a goose, and a goose and a cardinal, etc. All the possible pairs need to be rated. The MDS solution plots all the exemplars in multidimensional space. In this case, it is two-dimensional space. If two birds are often rated as being highly similar to each other, they appear close to each other in the MDS solution. Thus, goose and duck are physically close to each other in two-dimensional space, just like they are close to each other in conceptual space. What should be apparent from this graph is that the two axes have psychological meaning. The x-axis seems to correspond to aggressiveness or possibly size. Robins and sparrows are on one side, and hawks and eagles are on the other. The y-axis seems to correspond to domestic birds. Geese and ducks and chickens are at the top, and eagles and blue jays are at the bottom. The MDS solution provides a graphical depiction of the internal similarity structure of the concept bird. Figure 2.1. This is an example of a multidimensional scaling solution for birds. To generate this, the pairwise similarity among all pairs would have been gathered from raters. The algorithm plots an approximation of the underlying psychological space. The geometric approach makes several fundamental assumptions that are built upon the basic idea that psychological distance approximates physical distance. One of the main advantages of the geometric approach is that it is easily built into a computational system. The computational nature of the geometrical model gives the researcher a way to generate a similarity space for a participant. The computational nature helps to solve one of the problems with gathering basic similarity ratings. Namely, it provides some description of the internal structure of a concept that underlies the similarity ratings that the subject might generate. In fact, the multidimensional scaling solution should allow the researcher to predict the output of a rating task, or the decisions that a subject would make in a forced choice task, or the clusters that might form if a subject were asked to sort objects into groups. Because of this computational advantage, the geometric approach has been built into many models of conceptual structure. For example, in Chapter 4, we will discuss two representational accounts of conceptual structure. One of these accounts, the exemplar model, assumes that categories are represented by the summed similarity among all category members. The other account, the prototype account, assumes that categories are held together by the similarity of category members to a central abstract prototype. Both of these models depend on similarity, as calculated by the geometric model. The geometric model depends on its core assumptions. The fundamental assumption is that objects are represented in a psychological space that is roughly analogous to a physical space. Things that are similar are assumed to be close to each other. Things that are dissimilar are assumed to be psychologically distant from each other. Because of this fundamental assumption, the geometric model makes specific assumptions and predictions about the kinds of similarity judgments people make. Although these predictions are quite basic, they can sometimes be shown experimentally to be not always operating in people's judgment. What this means in essence is that although MDS and the geometric model work well to explain how people understand similarity relations most of the time, it cannot capture every case. It is a useful tool and a good way to understand psychological similarity, but it is not a complete account. Let's begin by describing a few of these assumptions and predictions. Much of the following was originally discussed by Amos Tversky in his hugely influential paper from 1977. The assumption of minimality. According to Tversky, minimality holds that the similarity between an object and itself is the same for all objects. If you measured the physical distance between the coffee cup on your desk and itself, it should be 0, and that should be the same result no matter what you are comparing. Another way of saying this is shown in equation 2.2. dii is less than or equal to dij. In other words, the physical distance between my coffee cup and itself is always less than the distance between my coffee cup and anything else. So if this is true in physical space, it should also be true in psychological space. The similarity of an object to itself, self-similarity, must be nearly 0 and the same across other self-similarities. But, as Tversky points out, this may not be true, as the probability of judging two identical stimuli is not constant for all stimuli, and judgments of similarity will vary, even if by a small amount. To the extent that people make errors in identification or recognition, one underlying possibility is that the minimality assumption does not always hold true. The assumption of symmetry. The assumption of symmetry is straightforward. The distance between one object and another is the same as the distance between the other object and the first one. In other words, a comparison between two things results in symmetrical relations. Comparison order should not matter. This is true for physical space. If you and a friend are standing at the bus stop, the distance between you and your friend has to be exactly the same as the distance between your friend and you. That is, it is reflexive and symmetrical. Another way to say this is shown in equation 2.3. Dij equals dji. Symmetry is a requirement of the fundamental assumption that psychological similarity is analogous to physical distance. If I conclude that a green apple is similar to a red apple, my ratings should not change appreciably when I am asked about the similarity of the red apple to the green apple. In other words, psychological space should have the same qualities as physical space. But of course, this is not exactly true. The classic examples come again from Tversky's work. He suggests that the judged similarity between North Korea and Red China exceeds the judged similarity between Red China and North Korea. The use of Red China probably sounds awkward to modern ears, but would have been quite common to subjects in the 1970s and refers to Cold War-era communist China. Furthermore, most people do not use metaphoric similarity in a way that suggests symmetry, just as Shakespeare writes that Juliet is the sun and not the other way around. We often say that a child is just like her parent and not the parent is just like her child. In short, these violations of the similarity assumption suggest that, for a complex stimuli at least, psychological space is not quite like physical space. The assumption of triangle inequality. Triangle inequality suggests that for three stimuli, the additive psychological distance between two pairs of stimuli must be greater than or equal to the distance between any one pair. Computationally, this is written as DAD plus DAC is greater than or equal to DAC. This assumption is less obvious on the surface than the two previous examples, but consider the following example, again from Tversky. Jamaica is judged to be similar to Cuba, and Cuba is judged to be similar to Soviet Russia, but Jamaica is not judged to be similar to Soviet Russia. One pair is similar as communist countries, the other pair is similar as islands, but all three are not that similar, and so the distance between the Jamaica-Russia pair might be greater than the combination of both pairings, which is a slight violation. Or consider a less complicated example that works in the other direction. Figure 2.2 shows a set of 9 circles that vary in terms of size and color. In a similarity rating task, some of these stimuli are similar and others are dissimilar. That is, it is easy to see a similarity between 2 circles of the same size or 2 circles of the same color. It is a little more difficult to know how to rate the similarity between 2 circles that vary in both color and size. According to the geometric model, though, these 2 dimensions should both enter into similarity judgments. Figure 2.2, triangle inequality. ABC is a shorter line than ADC, but when participants rate the stimuli that are shown, it can appear that the distance from ADC is shorter than ABC. On the right-hand side of the figure is a graph that shows 4 of these possible stimuli in XY space, with size as the y-axis and color as the x-axis. If psychological space aligns with physical space, then the similarity between A, B, and C should be greater than the rated similarity between A, D, and C. That is, A and B are physically close to each other, and B and C are physically close to each other. However, A and D are less close to each other in physical space, and so they should be rated as less similar than A and B. But if you inspect the actual stimuli shown in the left panel of figure 2.2, you will note that A and D are exactly the same size, and D and C differ in size but are exactly the same color. When asked to rate, people prioritize a dimensional match and give these pairs higher similarity ratings. The result is that in terms of rated similarity, the line going from ADC will seem shorter than the line going through ABC. Geometrically, This cannot be true, but psychologically it seems to be. The implication from a result like this is that psychological space may not always act like physical space. The contrast model. One of the biggest problems conceptually with the geometric model is that it only accounts for shared features or mismatched features. It doesn't have a good way to deal with the interaction between these. The contrast model, proposed by Tversky, includes a way to deal with shared features and distinctive features. According to this model, the similarity between two objects A and B is expressed as a linear combination of the common features shared between the two objects and the distinctive features unique to each class. Formally, this is given by the following equation. In other words, to calculate the overall similarity, SAB, one would first arrive at a measure of how many features they shared and subtract from that features that are unique to A and also features that are unique to B. The contrast model is able to predict asymmetric similarity because the distinct feature multipliers A and B are not constrained to be equal. As a result, the impact of distinctive features for one concept may be greater than or less than the impact of distinctive features for another concept. Relating this to Tversky's earlier example of North Korea and Communist China, North Korea would be predicted to be more similar to Communist China than the reverse because we assume to know more about Communist China. China has more salient, distinctive features than North Korea. Maybe that's not quite true anymore, with the heightened presence of North Korea in the news as a function of President Trump, and so asymmetric similarity is predicted. In general, the contrast model is most useful when dealing with the similarity among items when some items are more familiar, more important, or are at different levels of a hierarchy. The transformational model. One thing that neither model is able to account for is the kind of similarity that exists when two things are linked by non-featural aspects. That is, it is easy to see that two people might be similar, or that two apples might be similar. Both the geometric model and the contrast model can explain these types of similarity judgment. However, these models may not explain the perceived similarity between things like water and steam, or the similarity between a photograph of an adult and a photograph of the same person as a child. Yes, there are shared features between these things, but there is something else that feature-based models are unable to account for. Water and steam are similar to each other because one entity is transformed into the other entity. The relationship is not strictly based on features, but is rather based on the number of steps that it takes to turn water into steam. On that account, ice is closer to water than it is to steam because the ice to water transformation is one step, and the ice to steam transformation is two steps. Accordingly, ice may be more similar to water than ice is to steam. The transformational model is based on the notion that there is something similar about two things if one can be transformed into the other. Transformation is actually quite common. We transform water into coffee on a daily basis. We transform water into tea on a daily basis, or transform a slice of bread into toast, batter into cookies, natural gas into electricity. Some of these transformations are small and thus the entities seem more similar to each other. Some transformations can take place in a single step, but the surface features of the two things are very different from each other. Perhaps the best example is the transformation of a monarch caterpillar to a monarch butterfly. Most kids have seen examples of both, and in many schools it is common to have a small aquarium set up containing monarch caterpillars. The children can watch as each caterpillar forms a chrysalis and emerges as a butterfly. This is a remarkable transformation, and although the caterpillar is very different on the surface, we might appreciate that these are still similar. A monarch caterpillar is still somewhat similar to a monarch butterfly. Although this kind of similarity seems clearly intuitive for things that are known to be transformed, such as butterflies and coffee, it is also possible to show the effects of transformation on fairly abstract stimuli. A study by MI provided participants with simple patterns of symbols. Participants were essentially asked to rate the similarity between different patterns, Because the stimuli were created from a static subset of characters, the surface feature similarity was controlled. The only way to reliably make judgments was to base them on different kinds of transformation. Figure 2.3 shows 5 different kinds of comparisons. The first is identical pattern, where the similarity would be rated very high. The next is a mirror image. The pattern on the left is the mirror image of the pattern on the right. On the left, we see 5 filled circles and 3 empty circles. On the right, we see 3 empty circles and 5 filled circles. The next is called a phase shift. Here, you can see that the relative position of the 3 empty circles has shifted by 1 position from the pattern on the left to the pattern on the right. The reversal shows a complete exchange of characters from the pattern on the left to the pattern on the right. The most subtle change is the wavelength change. If you imagine the circles as peaks and valleys of a wave, the pattern on the left has a bigger wavelength than the pattern on the right. Figure 2.3, an example of the stimuli that were used by Amai in an examination of transformational similarity, with kind permission from Elsevier. Examples of stimuli that vary according to transformation: identical, mirror image, phase shift, reversal, wavelength. Participants rated pairs that differed by all of these single transformations as well as pairs that differed by multiple transformations. The main finding was that single transformation pairs were rated as more similar than multiple transformation pairs. The crucial aspect of this result is that the surface features were held constant. Participants had to base their judgments on how many steps were needed to transform one pattern into the next. Similarity and learning. One of the ways you can apply the ideas and concepts in this textbook is to try to use some of the ideas to help you learn new things or solve new problems. Let's take a look at how people use similarity to help them learn new facts and concepts. Similarity between learning and recall. Similarity affects how things are learned, for better or worse. When you are learning a new problem, a new task, or a new set of facts, you tend to look for similarities among the examples. You might even make an extra effort to maximize the similarity between learning and recall. For example, if you are using this textbook as part of a course, think about all the ways in which the class environment, your study environment, and your test environment are similar. You attend a lecture in the same room, at the same time, on the same day. You probably sit in the same seat. And if you can't sit in exactly the same seat, you probably try to find a seat that is near, for example, that is similar to your usual seat. When you study, you probably study in the same locations: your room, at your desk, at the library, probably at the same table. None of these things are related to the content of the material, but we still tend to go out of our way to make each learning occasion similar. In the memory literature, this is known as transfer appropriate processing, and it is part of a general theory about the interaction between learning and memory. Within the transfer appropriate processing framework, memory recall for items that a person is learning will be improved as a function of overlap in mental operations between the time when something is studied and when it is recalled. Having a class in the same room and studying in the same location can help by introducing subtle cues to increase the overlap and similarity between learning and test. There's a risk of making things too similar, of course. False memories also arise as a function of similarity. I will discuss memory errors in greater detail in the memory chapter. You're more likely to make a mistake in recall when the information you are trying to recall is similar to something else. One strategy to guard against this might be to try to maximize similarity between learning and recall when first learning about a new concept, but then induce some variability when studying for long-term retention. That allows the learner to take advantage of similarity while also building resilience. Similarity among category members. Another way to think about learning and similarity is to think about the similarity relationships among the things that you are trying to learn. When you learn a large group of similar things, you might be able to form an abstraction early on that captures the regularities and similarities among the things you are learning. In fact, Some research I carried out a number of years ago discovered just that. My colleagues and I asked our research subjects to learn new categories of things, usually cartoon animals that shared features, by having them learn to classify them into two groups. When we asked them to learn larger categories for which the similarity within the category was high, our subjects learned quickly and tended to form an abstract, ideal representation that they used to help them learn subsequent items. When the categories were smaller and or made up of things that were not very similar, they tended to learn less quickly and were also less likely to form an abstraction. Instead, they relied on learning individual category members. The idea that people learn new categories by abstracting general information can be used to facilitate the learning of complex new categories. If you train people to learn typical or ideal examples first, it may help them learn a whole set later. For example, Adam Hornsby and Bradley Love at University College London studied ways to improve students' abilities to learn medical imaging categories. Their subjects learned how to classify mammogram images into a cancerous tumor group and a no cancerous tumor group. They trained their subjects first, either on a full set of images or a set of ideal cases from each category. Idealized training meant that learners only saw very clear and obvious examples, whereas the standard condition learned a range of easy and more difficult cases. Hornsby and Love found that the idealized training was superior. These research subjects learned the categories more easily because the idealized training examples highlighted the critical features and also maximized similarity of the objects within the group while minimizing the similarity between categories. They concluded that learners, i.e., radiologists, should be trained on idealized distributions of information which minimize the saliency of ambiguous cases, but care should also be taken to expose the learner to an adequate range of stimuli. Some recent work from Robert Nosofsky's lab in Indiana University extended these ideas to try to understand how people learn about complex natural concepts that lack obvious ideals. In this case, they looked at how geology students learn about categories of rocks. Rocks can be assigned into basic categories like igneous rocks, sedimentary rocks, and metamorphic rocks. One of the things you need to learn in an introductory geology course is how to classify rocks into these three groups. These groups are defined by how the rock was formed, but not necessarily by how it looks. When Nosofsky and colleagues asked their research subjects to rate the pairwise similarity among 30 different rocks, 10 in each of the three categories, their resulting multidimensional scaling solution did not show a clear differentiation of the three categories, but rather suggested that people were making judgments on the basis of surface characteristics, namely lightness, darker or lighter rocks, grain size, i.e., granite versus smooth sandstone, saturation, solid color versus diffuse colors, and organization, linear shale versus lumpy conglomerate. Figure 2.4 shows their multidimensional scaling solution in four-dimensional psychological space, the psychological space of common rocks. Figure 2.4, the multidimensional scaling solution in four dimensions for a set of 30 rocks. Participants use lightness, grain size, saturation, and organization when rating similarity. In the figure, I, igneous rocks, S, sedimentary rocks, and M, metamorphic rock. If the categories lack obvious visual cues like these rocks do, how can you best teach people to learn the groupings? Nosofsky relied on an exemplar model, a mathematical model of classification that I'll discuss in the chapter on concepts and categories, to make some predictions. Using this model, they predicted that people will learn best if they are given some examples that represent the coverage of the category. That is, rather than teach people about the center of the category, the ideal, Nosofsky and colleagues suggest that the best way to learn about these kinds of complex and diffuse categories would be to learn about different areas of the psychological space. 2.1 Theory in the Real World. The work by Nosofsky and others tells an interesting story about how similarity affects the learning of new concepts. Many of the topics we have discussed point to the beneficial and sometimes not beneficial role of similarity in learning. In fact, researchers who study medical education have known for many years that doctors will learn about new diagnoses by recalling similar cases. For better or worse, we learn things more easily if they are similar to what we've done in the past. You can use this research and these ideas in your own academic career. For example, when you are learning new concepts for a class, you might want to emphasize some similarity early on to take advantage of transfer appropriate processing. You can sit in the same seat, follow the same routine, and study at the same time each night. And of course, you would want to look for similarity at the surface and deeper levels among the new concepts that you are learning. Try to find analogies and comparisons. But alongside this, you should also introduce some variability to make sure you can remember the right information in many different settings. When you are learning about a group of things that has a fair amount of similarity within the group, like the mammogram examples in Hornsby and Love, learning the idealized abstraction first could help you learn better. But for categories that do not have as much overlap, like the rocks in Nosovsky, it might be better to try to cover the whole range of the category with a few select examples first to learn about the variability and range of things in psychological space. In general, it helps to be aware of the role that similarity plays in learning new things so that you can use it to your advantage. Summary: I have placed this chapter on similarity at the beginning of the text because I think that similarity is a construct that is going to affect nearly every other topic that is covered. In chapters 3 and 4, I cover memory, semantic memory, and the psychology of concepts. All of these topics depend on the assumption that the basic cognitive system calculates similarity among representations, as we discussed at the beginning of this chapter. Memories are retrieved because they are similar to a probe. However, memory confusion sometimes results when different representations are too similar to each other. Categories and concepts are held together primarily by inter-item similarity. Similarity also plays a role in reasoning. As was discussed earlier in this chapter, inductive inferences depend heavily on similarity. In fact, the very core of inductive reasoning is the assumption that future events will resemble past events. That assumption can only be made with the understanding that the system making the prediction can calculate similarity. Similarity plays a role in problem solving as well, because problems can be solved on the basis of how similar they are to previously solved problems. I discussed the role of analogy in problem solving in Chapter 10. In this case, the assumption is that problem solvers are able to appreciate an analogous similarity between two different domains and to use that similarity to solve novel problems. Finally, similarity plays an important role in the psychology of expertise. Experts are those who have studied and worked in a specific domain for many years. As a result, experts have a rich knowledge base upon which to draw when confronting new problems and decisions. One of the primary ways in which they draw on that new knowledge base is to calculate the similarity in deeper ways than novices. In other words, a novice might appreciate the similarity among objects based on how they look. An expert might appreciate the similarity among objects based on how they are used or on how they might be used in a specific context. The study of similarity may seem like an aspect of cognition that is not directly related to the psychology of thinking, but I would argue that a complete understanding of the psychology of thinking requires an appreciation of the complexity of similarity within a cognitive system. Questions to think about. A common expression is, it's like comparing apples and oranges, which is supposed to mean that the things cannot be compared, but apples and oranges are pretty similar. Is there a better metaphor? What would the comparison of apples and oranges tell you? Can you name the three key assumptions, which are often violated, of the geometric model of similarity? And for each one, can you come up with other examples of how these assumptions might be violated? How does Tversky's contrast model address the shortcomings of the geometric model? How do you take advantage of similarity when learning new things? Do you try to group similar terms together? Do you study with the same people? Do you try to uncover deeper similarity relationships? If so, do you think that helps with recall? Why or why not?